Director of the VLab here in beautiful downtown Silver Spring, and I'm joined with John Chettel, who is our logistics manager for the VLab Forum, and we want to welcome everyone for our October edition of the VLab Forum. And we're very happy today to have Marc Chenard from the Weather Prediction Center of NCEP, along with co-presenters Phil Schumacher and Heather Reeves, although I think only Phil is joining us for this presentation. And their talk is going to be determining precipitation type from maximum temperature in the lower atmosphere, a very relevant and important topic for the Weather Service and all those interested in predicting precip and precip type. As you may remember, if not, I'll refresh everybody's memory. The purpose of these talks is to take a look at work, R&D that's being conducted throughout NOAA on things that may or may not eventually make their way into Weather Service operations or NOAA operations. And so our format is to get our presenters to sort of present content on what their project is in about 30 minutes, focusing on the research to operations aspects of their project, and then have about 30 minutes of question and answer where you folks who are online can, as well as those in the room, can ask questions and have a dialogue with the project lead. A reminder as well that these talks are being recorded, and John Chettel will upload the recording to the VLab Forum website shortly after, and you can share that link with your colleagues at your leisure. So without further ado, I would like to ask, Marc, are you there?
Yep, I'm here.
All right, so I'm going to hand it over to you, and please proceed.
All right, thank you for the introduction. I'll get underway here. So here's just the title of the talk. Again, I'm at the College Weather Prediction Center in College Park, Maryland. Worked on this with Phil Schumacher in Sioux Falls, South Dakota. Most of this, at least the beginning of this work, was done while I was in Sioux Falls as a forecaster before I came to College Park. Then a lot of the data manipulation and then some insights too into the conclusions here from Heather Reeves at SIMS and NSSL in Norman, Oklahoma. All right, so some of the background, just with precipitation type in general. I think as everyone knows, the impacts from snow, sleet to freezing rain can be vastly different. If you have an inch of QPF, whether that falls as freezing rain or sleet, even that, where there's just a narrow difference between those two temperature profile-wise, can have a significant impact to just the public and just in general, a significantly different impact. So it's important to accurately forecast which will be the predominant type if we can do that. And because the amount of ice and snow that you're going to get, of course, is going to rely on getting the type correctly. The current methods that are out there, a lot of the current methods, I know there's a lot of newer research that's being done that's hopefully improving upon some of the older methods, but just the basic precipitation type algorithms in general do not a great job, especially in differentiating between sleet and freezing rain. They do pretty good with snow and rain, but when you get to those mixed types, the skill drops way off. So it does at least bring up the question is for the need of probabilistic precipitation type. If we can't reliably say whether it'll be sleet or freezing rain, is it better just to give probabilities of one or the other? Especially given the different impacts, it's probably not a good thing to just pick one and go with it, especially if we don't have skill in doing that. So a little bit more overview. The goal of this is to use a large data set, and we're just going to produce probabilities of different precipitation types just based on the maximum temperature aloft. So kind of using just the top-down method in general. First you need ice in the cloud. That's the first thing to look at. Then as the hydrometeor or the liquid falls, or snow, does it melt? So you look at the warm layer aloft, both temperature and the depth. And then the cold layer below, if it does completely melt, can it refreeze? Is it cold enough below the warm layer to refreeze? This talk is just going to pretty much solely focus on that warm layer aloft contribution. Now, in general, if you're just looking at the surface-based cold layer, it's generally not significant. Of course, there is going to be, it does play a role, but only alone, it's not significant. If that was the only thing you were looking at, it wouldn't help you too much in determining P-type, whereas the warm layer aloft, if it was the only thing you were looking at, does have some skill. So that's the reason why, at least initially, you're just focused on the warm layer aloft. Then we also show that there's generally a strong correlation between that max temperature aloft and the depth. So just, again, to simplify things, just look at the max temperature instead of both that and the depth. So we used 500 meters, 600 millibar layer, and found the max temperature in that layer. The data set taken from Heather Reeves' paper from 2014, so it uses, what's that, winter months from 2002 to 13, and all reports from ASOSs within 35 kilometers of an upper air site. So it takes the report, correlates it to the balloon or up sounding at that time. We only included cases that had an elevated warm layer, and there were 422 freezing rain cases, 125 sleet, 34 snow. Then once we had all of those cases, we binned it every half a degree Celsius. So let's say you may have had, just to really simplify things, you might have between 0 and 0.5 C. Let's say you had 10 snow, 20 sleet, 25 freezing rain, then we just did probabilities from that. And then once we had just that basic, we then look at effects of uncertainty due to model error. So we take those observed soundings from the balloons and perturb them based on generally typical errors seen in a mesoscale modeling system. It was pretty much looking at the RAP, typical errors seen in it, and then perturbing those observed soundings, and then develop new probabilities off of that. So of course, just doing anything with precipitation type, there's going to be some sources of error. The first thing, and probably the biggest issue, is the unequal amount of sleet and freezing rain cases. Pretty much sleet is only, at least on ASOS, is only going to be reported at observation sites augmented by a human. Thus, you're going to have a lot more freezing rain in general than sleet. In this case, in this data set, you have 3.4 times more freezing rain than sleet cases. That's probably not the true distribution that we see in nature. And so if we're binning and then looking at probabilities, it's going to be skewed towards freezing rain because we don't have enough sleet cases because the ASOSs can't report sleet unless there's a human there. So we looked at different methods of normalizing the data. One thing we did is a 1-to-1 ratio of sleet to freezing rain, saying that sleet and freezing rain occur the same amount on average across the country. Then the one that we are going to focus on a little bit more that we decided to use was a 1.7 ratio. So it's pretty much saying that freezing rain occurs more than sleet. And this is based, there's not a lot of research, at least as of a couple years ago, that it went into much detail on this. So it's mainly a couple things out there and then just some subjective experience. And also, I mean, if you look at the temperature profile that supports sleet is generally narrower than the one that supports freezing rain. So with all that together, we probably end up with more freezing rain than sleet. So we did normalize the distribution to kind of fit what we would imagine is what actually occurs in nature. Another issue is that some of the freezing rain cases that we have in here may actually be the result of no ice in the cloud and not the warm layer. In order to try to thin out some of those cases, only cases that the temperature profile crossed the freezing line twice were used. So meaning that there had to be a warm layer and then a cold layer below it. Trying to rule out those soundings that are all below freezing but just don't have ice in the cloud. But even with that, there still could be cases that do cross the freezing line twice that still aren't deep enough to have ice. So there's probably some cases that did slip through that may be resulting in a slightly high bias in freezing rain at some of the cooler temperatures. Another issue is, well, even the observed soundings aren't perfect because the weather balloon is going to drift as it goes up. And like a 12Z sounding is usually launched closer to 11Z, but there's a window that it can be launched. And it's really, the exact time isn't really recorded or easily available. So given that we have even those slight differences, since sleet freezing rain is a pretty transitory P-type, you're going to introduce some errors just with that. And then just to reiterate, the goal of this, at least the data portion of this, is to isolate really just the role of that one factor, max temperature aloft, on p-type. It's not really intended to do, it's not really intended as a complete precipitation type strategy, because other things are obviously going to play a factor in that, including whether it can, refreeze as it falls through. So not a complete strategy. The data part of this section will focus on the max temperature aloft. I will go towards the end of the talk into more of a broad discussion. So just looking at the distribution of all of those cases that we had. So this is before I go into the bins. This is just the straight up distribution. You can see sleet on the left, freezing rain on the right. Kind of see where you do have the overlap and where you don't. For the most part, anything below 2C, there's not a lot of freezing rain. So pretty much between that half a Celsius and 2 or so is where there's not much overlap between the sleet and freezing rain. And then again, once you get above 3.5, it tends to be mainly freezing rain. But in between there, between roughly, say, +2 and +3.5, that's where you have your biggest overlap of the distributions. All right, so now looking at the bin probabilities that we had here. So this is the not normalized, and you can kind of see, I think it jumps right off, the issue that you would have by not normalizing because of you have way too many freezing rain cases, not enough sleet cases because of the ASOS issue. So in this case, sleet only maxes out at like 46%, and they're probably biased just too low in general. Now, one idea going forward that could probably actually help this, with MPing now, where you have a lot of users submitting precipitation type, that's potentially a way to add a lot more data than what we can currently do with the ASOSs. And so if you had an MPing observer that happened to be close enough to the ASOS, you could possibly use that to supplement, and that could increase sleet cases without having to do this normalization potentially. But as of now, we haven't done that yet. So looking at normalizing it, this is just normalizing it 1-to-1. You can still see that this is probably producing too many sleet cases because it's probably not a 1-to-1 normalization. It probably doesn't occur equally in nature. So you tend to get equal sleet and freezing rain probabilities over quite a large range. But if we go forward and normalize it to what we think is probably closer to what happens in nature, you see this is what ends up happening. Now again, even though we do have quite a few cases, it's still probably not enough, obviously, to smooth the curves out. So you do get these little valleys and ridges there in the curves, especially as you go out. There's still a decent amount in each of these bins, but you'll see as we go on, and we look at the perturbed soundings, that adds more cases, it ends up smoothing it out more. But with just the observed soundings normalized, you can see that even now the sleet, the highest probability you get is about 63%, and it's only between about 0 and 2C that it is the most likely precipitation type out of these bins. If we go a step further and say, well, a weather type isn't really dominant unless you have about a 60% probability, then there's a pretty wide range between 0.5 degree Celsius and 3 degrees Celsius where no precipitation type is dominant. It's pretty much the sleet, freezing rain are all below 60%. And then you really only have sleet dominant at least above 60% between 0 and 0.5 degrees Celsius, and freezing rain generally above 3 or 3.5 and warmer. So again, you have that pretty large range in the middle where the sleet and freezing rain probabilities are pretty close. So now let's perturb it a little bit. Like I mentioned earlier, if we say, based on the normal errors that we see in the RAP, let's run a bunch of perturbations on these observed soundings and see what the distributions do. So by adding all those cases, you can see the number of cases there in the first bullet increased dramatically, which results in a much smoother curves. So any differences from the non-perturbation and then the perturbed? Well, there are some, because we have, well, for one, the sleet probabilities decrease in general. It's now, if I go back between the two, you can see there was the non-perturbed, especially if we look at where this crossing line is, and then if we go to the perturbed, you can see it shifts left. So in general, everything broadens, so the lines get closer to each other in general, especially You don't notice it as much at the warmer temperatures. The freezing rain and sleet probabilities are pretty similar beyond 3.5 degrees, favoring freezing rain. But as you get closer in that 0 to 3 range, the sleet probabilities actually decrease, with the freezing rain probabilities increasing, suggesting that as you add in, even at forecast hour 0, some possible errors within the model, just because the range that sleet occurs is so narrow that the probability of it actually begins to decrease, even right off the bat at hour 0. Now, a couple other things, I guess, from this, just looking at what I have here. You still have decent sleet probabilities even as you get warmer. It stays around 30% from 3 all the way to 5.5, and then even 10 to 20 between 5.5 and 6.5. Now, some of that is probably, I mean, I've looked at some of these soundings just individually, not all of them, and some are pretty interesting, pretty different. You wouldn't really expect the P-type to be occurring from what you're seeing. Some of them could be a cold layer. So in general, I'd say that in reality, maybe those are too high, but the sleet probabilities at those higher amounts. But it suggests that, you know, it's not necessarily a very clear-cut. It's not really any clear-cut cases there. So if we go now, instead of just looking at, so pretty much what we had been looking at, if I go back, is just the cases that had a warm layer, cases that crossed the freezing level twice. Now going on, start looking at pretty much just all the cases. So that introduces snow back in there, because the reason why the snow probabilities are so low in here is actually because these are only ones that cross the freezing level. And so, or cross it twice. So in reality, there's going to be more snow cases, especially if it's like maybe just a low 500 meters if it gets just above freezing, or if it's hovering right around the freezing range. So if we go to the next one, we look at all the cases. One thing that stands out here that's different is, well, with snow on there, you can see how quickly snow drops off. And again, this is with the 0-hour forecast uncertainty in there. You can see even at below 0, between 0 and negative ½ degree C, so soundings that are all below freezing, only 75% of them ended up with the P-type of snow observed. And probably just because, you know, when you're that close, it doesn't take much of a model error to get a small warm nose, which then results in something other than snow. And then as you get above freezing, the probabilities drop pretty quickly, where even by ½ degree, you're down to 36%, and then they just keep going down from there. So the next thing is we'll look at a 12-hour perturbation. So before we were looking at 0. Now we'll look at 12 hours in the future. What's the common error ranges from the RAP? Perturb all of our observed soundings with that distribution. And here's what happens to our probabilities. Same number of cases, same observed data sets, same soundings, just with the 12-hour perturbation. If I go between the two, you can see it becomes pretty clear that sleet decreases even more. And so as we increase even more model uncertainty, just with that narrow range that sleet can occur, the probability of it given any sounding continues to decrease, with freezing rain continuing to increase a little bit. In fact, yeah, sleet never has a higher probability than freezing rain now. Sleet probabilities, the one thing you do notice though here, if going back between the two again, if you look out here at the warm temperatures, the other way, you see there's the sleet curve, dropping to about 30% by 3.5, and then down from there. The sleet probabilities actually do increase, suggesting, so again, the lines are really just coming closer together across the entire spectrum. And that kind of makes sense as you increase uncertainty. The ability to differentiate between a freezing rain and sleet profile is going to decrease. So you end up getting probabilities that go closer. I'm assuming if you went way out into I don't know, 10, 20 days, or I'm sure that everything would be 50, because that's pretty much what they're doing, is they're just combining out here, because as you increase the uncertainty, the models could be wrong, and so your probabilities are going to be similar. They probably won't come quite to 50, because freezing rain, like we said, if it does truly occur more than sleet, then it will always be a little bit higher, but you should see it actually converge to whatever that natural frequency is. But if we, let's see, anything else on this one? No, I think that that's pretty much what I had to cover for that slide. So if we go on to, this is really just summarizing those last two. So I'll just leave it up here for a second. Won't read through these again too much, but I guess the one main point is that it appears like it should be pretty rare to forecast only sleet, with the probabilities really maximizing between 54 and 63%. There's a very narrow corridor where sleet is that most likely type, so maybe a mix of sleet and freezing rain is best in most cases. Even freezing rain, it really takes until about +5 or +6 where it became the dominant, truly dominant p-type. So anywhere in that 0 to 4 or 5, it ends up getting pretty close, especially when you take into account some model error as you go out. All right. So now if we summarize it, things from a little bit of a bigger picture, and we look at maybe 3 factors to consider when developing these precipitation type probabilities. One, which is what we looked at in this, at least at the beginning, was given an observed sounding and an observed atmospheric profile, what is the precipitation type? So we know exactly what the atmosphere is, we know exactly what the profile is, so what's the precipitation type? Well, we looked at that. There's been a lot of other research on that. We have a pretty good idea, but there's even still some uncertainty left with that. That's not even perfect at this point. You could look at sounding. You could probably poll, especially if it was a borderline sleet freezing rain, you could poll probably 20 people, and I'm sure even 20 experts in the field, and you'd probably get different answers from some of them. So even with knowing exactly what the sounding looks like, there's still going to be some uncertainty in the p-type that ends up falling out of it. Size of the hydrometer is one factor among others that is probably not accounted for most of the time. So the second thing is, how do these probabilities change when we take model error into account? So that's what we started to look at in the second aspect of the data in those charts. And what we pretty much saw was that the probability distributions broaden. And so as you increase model error, your ability to differentiate, especially between freezing rain and sleet, ends up decreasing. Your range where sleet becomes dominant really becomes small. But even just in general across the entire distribution, the freezing rain and sleet probabilities get closer to each other. And this is the same reason why the snow probabilities are not 100% for temperatures below 0. I think for the most part, if you showed anyone a sounding that was all below 0 and you had ice in the cloud, it was going to be, it'd be snow. But if you take into account some model error, then that's not the case. And you can see even by hour 12 in ours, it actually dropped closer to 75%, just because of the errors, potential errors in the model. And the third one, which we didn't touch on yet, but it's definitely something to explore, I think, going forward is, so how do these probabilities change when we look at individual model biases? So not just model error, like in this case it was the RAP, but are each model going to behave slightly differently? If we looked at a sounding from, if you just look at the 3, NAM, GFS, and RAP, we looked at a sounding from the same event, even if the sounding looks the same, is the precipitation type that falls out of it going to be the same? Because, and I can just say from looking at soundings a lot and doing a lot of precipitation type forecasting, the answer is probably no. That each of these models has little things within them that are slightly different than the others that ends up resulting in different looking soundings, different looking warm noses, slightly different values. And so they could be forecasting synoptically very similar thing, but you're going to have to look at slightly different things to determine the p-type from each one. And I think one thing that's actually enhanced that thought is we had Dr. Kim Elmore from SIMS here at WPC not too long ago, and he just gave a talk on using random forests to determine precipitation type, and it was very interesting and it actually showed some promise. It was pretty skillful, but the one point of the talk that I want to touch on here was that he looked at pretty much you generate the random forest as just a bunch, looks at a bunch of different variables and goes through a process and trying to determine the p-type. So if you look at the forests he generated them each individually, so he did a different one for the NAM, GFS, and RAP, and showed, oh wow, we have a great increase in skill from the current method. But then he said, well, let me take the forest at the GFS and put it in the NAM and, just mix them up. And there was a big decrease in the skill, especially in those mixed p-types, freezing rain and sleet, which I think adds to the thought that, the models aren't all the same. So if you are trying to do a precipitation type by blending models, but only looking at maybe factor 1 here, or even if you look at factor 2, you're still not looking at everything because each model is going to be slightly different. You could have a warm nose of 3, you could have a cold nose of 1.5, you could go through the whole top-down method, but each of the models should actually be slightly tuned slightly differently, just because of the way that just some systematic biases that are within them that really come out in these fine-tuned in cases like this that are very sensitive to just small changes. All right, so some of the applications, Dan Baumgart, Andy Just, they really were the big developers for a tool that uses probabilities like this with the probability of weather type tool. They had the initial idea. They pretty much had put a lot of the work in getting this going in Central Region to the point where I know we were using it in Sioux Falls before I left. Now it's involved in the Central Region Forecast Builder, the process now to give a first guess for the grids, and a similar methods, I think, being developed for the national blend of models. So pretty much it just takes the top-down method and generates probabilities of snow, freezing, rain, and sleet. Then those probabilities are used to derive snow ice amounts from the forecast QPS. So for example, if we had 1 inch of precipitation in a 6-hour period, and if the probabilities that you see on there, 25% snow, 50% sleet, 25% freezing rain, were the probabilities on average through that 6-hour period, then that's what you would end up getting. You'd have, if you've seen the 10-to-1 ratio, you'd have 2.5 inches of snow, 1 inch of sleet, and 1/4 inch of freezing rain. So instead of just doing picking one and saying snow is going to be most likely in that period, or sleet, it breaks it down so it gives you at least a distribution, a range, so you get a little bit of everything, but based on at least some scientifically derived probabilities. But and going through, especially on that last slide, what I think maybe could be added to tools like this to increase the skill is not only do you incorporate uncertainty due to a p-type from factor 1, which is given in observed sounding what is the p-type, but you also need to look at factor 2, which is model uncertainty, and maybe down the road even at factor 3, which is each model is going to behave a little bit differently. But if you can come up with reliable probabilities and use them in this tool, it'd make it much easier to derive snow and ice amounts scientifically sound way, and will allow increased consistency in general across the Weather Service. So as of now, I know we're on the way towards national blend and better starting points, but there has been a pretty big consistency issue. It's gotten better recently, but still there with snow and ice accumulations. And probably the biggest reason is just that there's so many different tools and methods for generating these grids in the field. And so if you have different tools, different ways of people doing it, makes sense that you're not going to get the same answer. Now I'm at WPC. Well, at WPC we produce 24-hour snow ice totals that are then disaggregated into 6-hour grids. However, if you have mixed precip, it's going to be pretty tricky to use these in GFE or in your forecast, because you need to make sure that your weather grids are matching the snow and ice that you have. Since WPC doesn't produce weather type guidance, it really makes it difficult to use. So even if WPC collaborates and gets everyone on the same page with these snow and ice, the current sets of tools don't really make it easy to use it. You probably have to find a way to work backwards from the amounts to come up with weather grids, and just not probably a preferred way of doing things. So it brings the need probably of develop the link between WPC snow ice forecasts and the GFE forecast process at the local office. I mean, one thing that, you know, it seems just by going through this research that seems to make sense is maybe having just probabilities that are from within the model probabilities of weather type, whether it's done post-processing statistical way or actually within the model using microphysics and just an actual output of the model. But whatever way is eventually decided on, I think it seems to make sense to have precipitation type probabilities from the various models, which then could be blended maybe as desired by the forecaster. Again, you include whatever things in there that we end up deciding is most skillful. Then these probabilities, I still think it would make sense with you know, with WPC looking at all the stuff, looking at large-scale model preferences. You know, if WPC had these, tweak them based on the model preferences, send out to the field, then you end up having a national probability precipitation type for everyone in the entire country that then can be fine-tuned locally. So this kind of process would seem to simplify things quite a bit in that, you know, you no longer have everyone doing different things. I know the national blend should help in getting towards something like this, but just in a way where you can derive these probabilities across the entire country and then locally tweak them. You always have, you know, surface temperature, maybe not the best in the raw model sometimes, and you know, local officers are going to know certain biases of those. And so you'd have some way of adjusting these based on the actual surface temperature, but that shouldn't be that difficult to do since you can track the P-type all the way down to the surface and just use probably pretty simple tools to adjust based on what the actual forecast surface temperature is. So pretty much just summarizing, I guess, going through is looked at 3 factors that consider probably important for precipitation type. I think we're making a lot of progress on the first one, which is, you know, realizing that there's uncertainty even with an observed sounding, but then going forward in increasing the potential of model and even individual model errors, how those alter the probabilities. And then eventually getting to the point where we have probabilities that are easily produced, maybe even just output of probabilities from the model, so you don't have to be running these tools at each office or everywhere. And then you can easily blend those as desired, ship them out so that everyone has that starting point with then just adjustments from there. So I think that is all that I have to say for the talk. So I guess we can I can pass it off and see if we have any questions or any discussion.
Okay, Mark, thanks very much. Very interesting talk. Lots of ideas to consider there. So switching to the Q&A portion, I would remind folks who are on the GoToWebinar, please use the raise your hand feature if you'd like to ask a question directly to Mark or Phil, and John Chattel will unmute you for that. Or you can use the chat feature to ask a question as well, and John will relay that question to Mark and Phil. So, John, do we have any questions in the GoToWebinar?
We don't.
We do not. Okay. In the room. Go ahead, Dennis.
Hi. Could you please explain why you were excluding the cases where you said there was ice in the cloud? Just please explain that. Ice in the cloud.
Actually, yeah, we were excluding cases where there wouldn't be ice in the cloud. So, like if you're looking at the top-down method, I can go back to the slide, or I'll just explain it. If you're looking at the top-down method, if you don't have ice in the cloud, then you're not going to have sleet or snow. It'll either be freezing rain or rain. So, since we were looking at mainly differentiating between freezing rain and sleet, we were trying to require that there be ice in the cloud. So any cases where we thought there wouldn't be ice, we're trying not to include in here.
And how do you determine if there's ice in the cloud?
Well, and that was one of the potential drawbacks at the beginning of this, is that it pretty much used a basic method of requiring the atmospheric profile to cross the freezing line twice. So a lot of the time when you get freezing rain or freezing drizzle from when you don't have ice in the cloud, the whole profile is below freezing and you're just not cold enough to have ice in the cloud. So we only looked at cases that did cross the freezing line twice. So that they're only cases that had a warm nose. Now there probably could be a couple cases in there that snuck through that did have a warm nose, but still weren't deep enough to have ice in the cloud. So it's probably not a perfect data set, but we did take steps to try to mitigate that problem.
So all your cases had below freezing temperatures in the boundary layer? Near surface?
Yes, at the beginning. So like the charts that I showed, if I go back, all of these charts did, because we were looking at ones that crossed twice, and then they were below freezing in the boundary layer. Now, when we started looking at all the cases, some of these may have been a little bit above freezing at the boundary layer, but no, we didn't look at anything that was, well above at the boundary layer. So we pretty much isolated just trying to isolate just the warm nose aloft contribution.
Okay.
Okay, thanks. Bob?
Yeah, this is obviously a conditional forecasting scheme and so forth. You may have mentioned it, but I didn't catch exactly what is the condition. In other words, in order for probabilities to be defined here, you have to say, well, if this condition is met, I'm going to make a forecast, or if the condition is not met, I'm not going to be. So what is your condition?
In this case, it's pretty much, again, pretty much just isolating that one factor, so having a warm nose aloft. So this is pretty much looking at the condition of, especially on these cases, is if there was a warm nose aloft and you're below freezing at the surface,
and you got a definition. And you got a definition for that, so you know exactly how to do that. Is that right?
Yeah, well, that's where at the beginning where we, in order to isolate cases to the best that we could, we were only looking at the warm nose aloft. So that's why we removed cases that may have not been deep enough to have ice. We removed cases that were too warm in the boundary layer, so they would be rain. Removed cases that were all below freezing, so it would clearly be snow.
Yeah.
So yeah.
Okay, well, I asked this because if anybody else is going to use the technique, for instance, you have to have a very definite, it has to be defined very carefully as to what is going to be your condition. The other question, I guess what you're doing is mixing in the long run, you're mixing cases where both freezing rain and sleet are observed, and at stations where only one of them is observed. Is that right? And that's the reason then that you are maybe making you're boosting one up by a certain percent because of that, and so on. That seems kind of a pretty tricky business to me. As to what percentage, I see that slide right up there. You've got 0.6 in there, or something. Did you, for instance, take only the stations where both were observed, and then find what the ratio was for those stations, and say, well, okay, that's it?
We did not do that. That is a good idea. I think that would be interesting to see what that came out of. I'm not 100% clear that we'd have enough cases to significantly say, but it probably would be as good or as useful as this. Another method that just became aware of recently that I think deserves some investigation is again looking at MPing, where those are reported just because of the nature of how that's reported. There really shouldn't be a bias in those reports of sleet to freezing rain. And I know that data set does exist, and so potentially looking at that and seeing the distribution. That's probably the step that I would take next to help with the issue that you're describing.
Yeah, well, those things are pretty important when you're talking about probabilities.
Yeah. Now, I'd argue that obviously, if you're doing a method with probabilities, you need exact probabilities. Now, since we're looking at one aspect of it, I would not recommend that you plug in the probabilities that you see on this table or the probabilities that you see on that table exactly, since this is just one factor. The main thing that we looked at into this and that came out of it was the fact that this, just in general, the sleet and freezing rain difference is maybe not as large as some assume, and that as you introduce model uncertainty, your distributions broaden and become closer to each other. So that was probably the most important conclusion that we saw out of it, not necessarily the exact number of the probability, but how the distributions evolve as you introduce uncertainty.
Okay, thanks, Mark. John, do we have any questions? We don't. We do not. Okay. So,
well, I'm going to ask.
Well, wait, I get a chance.
Oh, you get a chance.
Yeah. So, Mark, I'm taking this in a different direction. Okay. So, sleet. So, first question is, and this is out of ignorance, I'm asking, ASOS does not detect sleet. Why is that?
It's because the equipment is not capable of doing it. I know there's some work on potentially adding that to them, but as of now, the ASOS will report freezing rain, snow, rain. It does report unknown precip, which you may be able to assume could be sleet, but it's not a deterministic sleet output. So as of now, just the equipment and the ways that what the ASOS has to determine p-type does not have the capability of determining sleet. But I do think I have heard somewhere that may be changing before too long.
So then what is the sleet observed as? Rain or freezing?
Yeah, right. So Bob, so when you do have sleet at the ASOS site, what is it, the default that it labels it as?
It may be unknown precip, UP. I think that if you all looked at ASOS or OBS, you see UP in there a lot. But it's not necessarily sleet if it says UP. Probably more often than not it is, but it is not a guarantee that when you see UP that you're getting sleet. So it wouldn't be necessarily correct to use UP as sleet.
It doesn't default to snow?
It may be snow. I mean, I'm not an ASOS expert, but just from what I do know, a lot of the time there will be UP in there, an unknown precip, because it's not fitting the definition of any of the things that it has assigned to it, because sleet is not in its output. Like the mechanism that is determining the p-type looks at different factors of the thing falling and then puts it into categories, and sleet is not one of those categories. So if it doesn't fall in any of them, which sleet wouldn't, then it would be UP. If it falls into the snow, then, or if it's close to the snow, then maybe it will be snow.
Okay. So, but I got to believe that somebody's come up with some sort of device to detect sleet, but we just can't afford to install it at our ASOS sites or something like that.
Yeah, I think that's partially what it is.
Okay. So next question. So this all grew up in Central Region. Sioux Falls, was that the epicenter of this? I mean,
a lot of it was in the beginning of the tool was there in La Crosse. I think I have that on one of these,
yeah, you said La Crosse too. So from an impact standpoint, if you're forecasting winter precip in La Crosse or Fargo or Sioux Falls, where do these rank in terms of problems? Sleet, freezing rain, and snow. Are they equally impactful and equally important, or does the sleet forecast really say, oh, that's not a problem? I mean, how does Weather Service customers and decision makers are affected by the differences in the precip types, frozen precip types.
Yeah, I mean, I guess if I focus on the sleet and freezing rain issue, since that tends to be the biggest issue right now with the current methods, there can be pretty significant differences. Sleet in general, although depending on the road surface and the type of sleet, can still produce some slippery conditions, but sleet is usually not going to be as significant of an issue unless you have an extreme amount of it compared to freezing rain. If you have a 1/4 inch of, or let's say 1/2 inch of liquid, and that all falls as sleet, you're looking at maybe an inch of sleet on the ground. Whereas if that falls as freezing rain, you're looking at a 1/2 inch of ice. Ice will accumulate on trees, ice will accumulate on power lines, sleet generally won't. And so you're going to have a lot bigger issue of tree damage, of power line issues than you would if it was sleet. So I think the biggest difference in impact generally is between sleet and freezing rain, and unfortunately that's the most difficult to determine between.
Okay, all right, fair enough. Other questions? Now, Mr. Miller.
Now I'm allowed to go.
Now you're
again.
allowed. Yeah, I've had my.
Okay, I actually have 2 more. What are the parameters in terms of time for what you're calling one case? Is it frozen precip during 1 hour at a ground station, or is it like for an event, like, you know, a 3 or 4 hour sleet event or something? How do you determine what a case is?
For these, it is just like an hour, but it's not like consecutive hours. So in order to define event, I have to go back and to get you an exact number, but I believe it was maybe, say, 12 hours. So you kind of didn't want to say, well, we had sleet this hour, then this, or sleet again, so that you'd have a bunch of the cases from the same event that could skew the data set. So it's really just an hour within the event. I could get you some more info on the exact details, but that's pretty much the basic of it.
I don't need more details. I just wanted to get a sense for whether, like, if it sleeted for 6 straight hours, did that count as 6 cases or just 1 case?
That should be just one case.
Yeah. This is Phil. It has to do with the fact that it has to be within an hour of the launch of the sounding and within 35 kilometers of where the sounding was launched from. So that way, in theory, the sounding is representative of the precipitation type that's being observed.
Okay. Yeah, that makes sense. And the other thing I was wondering was, in one of the slides you were talking about making forecasts for the 3 different types of frozen precip all at the same time. You would forecast a certain amount of sleet, a certain amount of snow, a certain amount of freezing rain. And I'm wondering, does that really make sense? Would you really expect all 3 of those at once, or should it be an or forecast and not an and forecast?
Yeah, I mean, that is an interesting, and I think that is an interesting dilemma, I think, when considering our forecast and what exactly should we be forecasting. Because in reality, although over a 6-hour period, maybe you could get a little bit of each, but you're right, in reality, at any given hour, you're probably going to have at least a majority of one P-type over another. And so, but what this is trying to do is limit, it's pretty much more of a probabilistic approach of getting to a deterministic forecast. And so you're right, most likely we're not going to have enough of either. So like if this was our forecast, that's probably not what's going to happen exactly. But you're probably limiting your errors on each one by doing it this way. But is that the best? I'm not, that's probably another discussion is, are you better off going all in on the forecast, but then if you're wrong by a lot, or doing it this probabilistic way, and you know, and just because of the difference in impact, that's the one reason why we were trying to looking at this way of doing it, because you know, if we think that it's probably not going to be freezing rain, so let's leave that out of it, and then it turns out being all freezing rain or a majority of freezing rain, then we messed up a lot, and the impacts are going to be significantly different than had we gone about it this route would have given a better heads up.
This Phil again, and one other thing is right now in NDFD our QPF is 6 hours, and so that makes it you almost have to bin it in some way or another. But I think, like Mark said, is right. This is probably a discussion we need to have at some point as we go forward. Probably as they develop the NBM more towards different precip types.
Okay.
All right.
Thanks.
Thanks. John, any no questions from the...
No questions from the remote.
Okay. All right. Well, thanks, guys. Oh, one more question. So I wasn't quite clear. In terms of research to operations here, so you mentioned this probability of weather type tool. So that's being used already at the WFOs, or some WFOs. But what you're really saying is that ultimately things that would fall out of this research should be applied to the national blend of models?
Actually, as far as I believe that, as far as I've heard, and again, Dan Baumgart and from WFO Lacrosse leading this effort, the POWT method is the method that is being developed right now for the national blend of models. So it would be a similar method, but again, it's currently really just using the observed, so it's not taking into account any individual model biases or model error as you go out. So this research also delves a little bit into potentially looking into adding those factors based on some of the results. But the basic POWT tool, as it is being worked on as of now as the way that the national blend of models will handle p-types.
I see. Okay. Okay. So this all has informed that, and presumably would continue. So so are you guys continuing to work on this as a research project, or this is pretty much wrapped up now?
So the base part of it has been wrapped up, but adding, looking more in depth maybe at some different model things and how model errors, looking more into that factor is probably something that can be explored more, as well as potentially looking at the fact that we have this huge database of reports from MPing that may allow you to increase the data set some. Both of those things. Right now, we're not actively doing that, but something to consider pursuing. Okay,
and so along with MPing, I mean, has thought been applied to looking at state and local highway measurements of these things if they exist, or power observations from power companies when for freezing rain and so forth?
Yeah, I guess the main difficulty part of this also is not just the obs, but also the observed profile. So since we're using the soundings from the balloon and they're just valid they're just instantaneous, it's hard unless you can get an instantaneous p-type report. It'd be hard to really expand too far with stuff like that.
Right. All right, very good. So again, thanks, folks, for putting this together, the work in general, and presenting it today. I think it's definitely good stuff that's been the fruit of a lot of labor on a lot of folks, and hopefully, like I said, it will, if nothing more, inform what goes forward for the National Blend of Models. So thank you very much. Good job.
Thank you.
And a reminder that, again, the recording of this will be uploaded to the VLab Forum website shortly after the conclusion of this call, and you can share that with your colleagues when it's up there. And a reminder that in November, coming up next month, on November 16th, the topic will be the aviation forecast verification tool, to be presented by Tabitha Huntman. we won't have we will not have a forum in December for Christmas and the holiday season. However, in January, yours truly will be providing an update on the virtual lab itself. We haven't done that in a while, so we want to share where we're at with the VLab to the broader audience. And then in February, Bill Rasch will be presenting the Weather Archive and Visualization Environment, the WAVE as it's called. So hope you can join us for those. And again, thanks everyone, and have a good rest of your day.